Okay, hello everyone. Before we start today, I want to acknowledge the Indigenous peoples of all the lands that we are on today. While we meet on a virtual platform, we can take a moment to acknowledge the importance of the lands, which we all call home. We do this to reaffirm our commitment and responsibility in improving relationships between nations and improving our own understanding of the local Indigenous peoples and their cultures. So my name is Autumn Sipis. I am the project manager for the Canadian Coalition for Green Healthcare, and on behalf of the coalition, I would like to welcome you all to today's webinar, Displacement Ventilation, Rethinking Indoor Air for Health and Climate. This webinar is being delivered as part of the coalition's Preparing Canada's Healthcare Buildings for Net Zero project, made possible with an investment from the Government of Canada's Low Carbon Economy Implementation Readiness Fund. Throughout the webinar, please use the chat function for any technical issues you may be experiencing or any comments you have. Try to use the Q&A function for any questions you have regarding the presentation, and our panelists will be answering questions at the end of the event today. We will also be recording this presentation, and the recording will be sent to all registrants and available on our website and YouTube channel at a later time. And then here just shows you Q&A, chat, recording. Okay, so we have 4 presenters with us today from the Displacement Ventilation Emergence in Healthcare, or DIVE, Research and Engagement Project. We have Alex Hutton, who's the founding principal of Sword Fern Strategic Sustainability. She is a professional engineer specializing in sustainability and change management with a focus for over 10 years on energy and carbon management within the healthcare sector. Alex has been an advocate of DV for decades and has participated in the energy modeling aspect of 2 DV projects in the BC healthcare sector. Alex is also the project manager for the DIVE project. We also have Greg Allen, who is Senior Associate of River Court Engineering. He has worked on advancing sustainability for 45 years as a designer, builder, community planner, inventor, researcher, and consultant. Greg has designed dozens of DV systems over the past 40 years and is the primary author of the DIVE research deliverables. And we have Tarek Amlani, a mechanical engineer with almost 2 decades of experience. A collaborative leader, has played a pivotal role in the delivery of some of the most complex healthcare projects in North America, including North Island Hospitals Project and the Kelowna Vernon Hospitals Project. Tarek is the Global Health Engineering Lead in Canada for Stantec and has a wealth of experience designing healthcare facilities with DV. He is a key partner and contributor for the DIVE project. Last but not least, we have Sabah Ali, who brings extensive experience in energy efficient building design with 13 plus years as a mechanical designer and over 11 years in the healthcare sector as an energy coordinator and now energy and emissions project manager at Vancouver Coastal Health. He leads the integration of low carbon resilience and retrofit projects and was the lead mechanical designer for Canada's first DV project at Nanaimo Regional General Hospital, still one of the country's most energy efficient hospitals 15 plus years later. Sabha is the technical contributor for the DIVE initiative. Okay, now I'm going to pass things off to Alex to get our presentation started.
Alex, you are on mute.
Thanks, Sabah. I'll say again, I'm going to invite you to pause for a moment here. I was reminded of the expression drinking from a fire hose in a meeting earlier this week, and it made me think of a different metaphor, maybe drip feeding. This is a big topic, and the reality is it's not something we can unpack fully in 1 hour. We can't convey all the experience and expertise of my co-presenters in 1 hour. So I'm going to invite you to sort of listen, relax, trust that some things will land, some things may not, and that's okay. You can come back and ask us more questions if you don't get them answered today. There'll be a breadcrumb trail of reports and resources and things that you can follow up on if you like. and hoping that whatever does land will create some ripple effects in terms of maybe questions that it will lead you to answer or ask yourself and ask others and so on. And to this idea of trying not to have you drink from a fire hose, there's gonna be times when I have text like this and references show up and I just pass by them. That's so that you can, go back and digest them further later if you want. So, not only is this a big topic, it's also sort of part of a bigger, longer journey. We're kind of building on work done by others, and I anticipate that the work will continue beyond the sort of timeline of this particular dive research and engagement that Autumn mentioned. And also we need a lot of people. So we feel that this proverb is apt. If you want to go fast, go alone. If you want to go far, go together. So we really do need a lot of different perspectives and disciplines and people involved in this. So we're also welcoming you to get involved if you are so desire. And I want to acknowledge that already in the work we've done to date, there has been many contributions from people and organizations in the form of funding, in the case of the top row here, and in terms of expertise, in-kind support, and so on with the other ones referenced here. I just want to note that this is not exhaustive. There are other contributors, and I also want to be really explicit that I and my co-presenters are not speaking on behalf of these organizations. This is a very nuanced topic. There's a lot here. It would be unrealistic to think that we are on exactly the same page with, what we think are the next steps for DV, what we think are the appropriate applications and so on, with all the people in these organizations, let alone the individuals that we've been interacting with. So just want to make that clear. So I thought it might be appropriate as an entry point for those who may be very new to this idea of displacement ventilation to provide an entry point through this idea of older, structures and dwelling types that have been used across the land that we now know as Canada. Many Indigenous cultures used shelters similar to this drawing here. Some were sort of temporary summer housing, some were used in different seasons, and so on. But the point is that some of the underlying principles behind DV, namely the buoyancy of warmed air and the idea of contaminants leaving with that warm air, and that warm air leaving at a high level, being replaced by cleaner air that comes in the ground level. These are some of the sort of fundamentals of DV that have been recognized by people for a long time. And I actually lived in a structure like this for a few months about 25 years ago when I was working on an organic farm in Spain. And so I want to try and give you a window into that real experience of, sitting there and feeling this like gentle flow of cool air coming in. And at the time I didn't know about DV, so I wasn't thinking about it in those terms. But in hindsight, I can notice how, the warm and contaminated air were just moving up and out. So these are some of the fundamentals. And another aspect is that often comfort is maintained largely independent of the ventilation, for example, by radiant heat. So we'll come back to that later. So you may be thinking, well, geez, TP is a far cry from a hospital. Well, yes, you're totally accurate. And some of these same principles have been at play since, Nightingale era. Her and her contemporaries were actually quite wise about what was happening in buildings. And, in this case, many of Nightingale's designs were harnessing displacement ventilation in a natural ventilation form, which is not really what we're focused on here, but similar concepts. Operable windows low and high allow that fresh air, the outdoor air, which is really what we need for health, to come in, pool across the floor, rise up due to the heat of the person, come right to their breathing zone, and then go up and out. So Nightingale's first canon of nursing was keep the air the patient breathes as pure as the external air without chilling them. And in some ways that, remains the beauty and part of the challenge of DV, which has been implemented well by many people at this point. So I'm going to invite Greg to give us, with his extensive years and a broad window of time, give us a bit of a snapshot into, Nightingale's era versus hospitals today, which are obviously more complex.
Yeah, so 2 centuries ago, were quite intuitive about how we designed buildings so that they did cause the contaminants and heated air to rise and leave the building while bringing in fresh air at the lower levels. So it's a very obvious proposition. So how did we get to the point where we find it questionable to use and have neglected it, particularly in North America, as an option for ventilating healthcare facilities? Somewhere about my birth, we began to have air conditioning doing more than the movie theaters, but moving into the commercial and institutional buildings. And this consisted of having a compressor that created refrigeration effect, which caused the air to be cold. And that cold air could be delivered through ductwork. Well, the most convenient place to put ductwork was up in the ceiling. And so we invented the drop ceiling to accommodate all of the circulation of the air in these large complex buildings. Then they could deliver the quantum of cool air required to make it comfortable in the space. So this led to designing systems that attempted to mix the air as perfectly as possible in the space by circulating through grills at the ceiling level, spreading across the ceiling level, and then circulating in big circles to carry the contaminants out. Of course, what this meant was that if there is a contaminant source in the room, it gets spread evenly throughout the whole space. So intuitively, again, it would seem not an ideal proposition from the standpoint of removing pathogens that are breathed out by occupants. That's the short history of where we are, and we're trying to bring some science to the ability to design displacement ventilation systems that meet all of the requirements and actually improve on the performance of ventilation in healthcare.
Awesome. Thanks, Greg. So we've touched on some of these early applications. I won't go into some of these, but I'll just touch on the fact that when DV displacement ventilation sort of got given its name formally, was actually in Scandinavia, in countries where they were using it in industrial buildings to protect the occupants, so to remove those contaminants away from the occupants. And so just want to be clear that while a lot of energy savings are achieved with DV, and we're going to unpack that, the driver is really to optimize occupant health and remove contaminants. So I just want to note also that we're building on a significant research effort here that Stantec and Mazzetti partnered on. And again, these are sort of breadcrumb trails of things that have happened. And then this Nanaimo Regional General Hospital Emergency Department that Sabah worked on, he'll talk about later, opened in 2012. There's also two other examples of DV in BC. Willow Pavilion at Vancouver General Hospital campus, which Stantec also worked on. I believe Tart was involved in that one. We might reference that later. And then there's also a Willingdon Creek long-term care facility in BC that Stantec worked on. And then myself, Sabah, and Greg all had the opportunity to work on the business case of the New Surrey Hospital and Cancer Center. And we did an innovation study that brought forward DV and explored it quite rigorously, including some great costing analysis that was done. And that's part of what spurred us to say, hey, let's see if we can seek some funding to keep building upon that huge effort that Stantec and Mazzetti did and see if we can move it forward. So fast forward, here we are, and that's part of what we're talking to you about today. I just want to acknowledge that, even though DV has been around for 40+ years and has been used widely in many countries and many sectors, it has been used in healthcare in Canada, and it's also been used in healthcare in other countries. It's understandable that the adoption has been slow. Healthcare is necessarily risk averse, and so it makes sense that this normal, we know that all innovations, and by this point DV is not an innovation in the sense that it's been around for 40 years, but it is still an innovation in the sense that it doesn't have the uptake that we would hope for. And so it makes sense that this curve has perhaps been even further elongated in healthcare. And so we hope to help show the relative advantage, the compatibility, the trialability, observability, and less complexity that DV actually does offer. I want to just give you briefly a bit of the whole picture, because we're giving you an entry point into this topic, and we can't cover it all at once. But sometimes it helps to have a bit of a bigger picture to place what you're learning into. So I'm going to try and give a little bit of the nutshell that we will then try and unpack. And if our timing is well done, then we will unpack quite a lot of it, but not all of it. So we've covered quite a bit of the context already. There's this current state of, yes, DV has been applied. It has been applied in Canada. It's applied elsewhere. And yet there could be more. There could be more applications. And a future state of DV that we foresee, after we get over these various hurdles, one key part of that we envision is that DV could be implemented in a way that can justify lower ventilation rates. And so that's a big topic that we will unpack a little bit. And there's various pathways. There's not just sort of a one way to get over these hurdles. So we're exploring a number of pathways. And so the benefits of DV are significant, and the benefits can also be even greater in that future state that we're talking about. So already with the examples we have, we already know that DV can save a significant amount of energy. It can reduce carbon significantly. It can improve infection control. It can improve occupant health. It can improve thermal comfort. It can improve climate resilience, and it can be potentially cost neutral or cost savings, or a slight, the cost one is a bit, depends on how you design it. And yet this future state, where we're able to harness the infection control benefits of DV to its fullest extent, where we would be able to do DV with variable and sometimes lower, sometimes higher rates that are more appropriate, we think. And once that's fully proven and demonstrated, that will achieve much more energy savings, much more carbon savings, and has the potential for a huge capital cost savings. So in a time right now where there's a lot of pressure on costs, there's a lot of pressure on infection control, there's pressure on energy and decarbonization, this strategy has the potential to really be a game changer. So the barriers, if it's so great, why hasn't it been applied more to date? Well, there's a variety of barriers. Some of them represented by the clouds here are really myths and misconceptions. So we're hoping to shine a light on those, evaporate those clouds with some of this work. And there's still sort of real, more tangible barriers in terms of some unknowns that need to be clarified further, capacity that needs to be built, and so on. So there's a perception that DV is not permitted by code. On the contrary, and we will unpack that, that DV is very expensive. Well, again, it depends how you design, but we disagree. We believe it, especially in this future state, holds the potential for significant cost savings. That overhead supply of DV is the only way it can be done. We'll unpack a bit that DV can be delivered from the ceiling and falling down a wall or a surface, coming along the floor and having the same effect as if it were, the grills lower at the ground level that we're more used to. This lockup effect that was sort of came into effect due to a study, we can unpack that and why that effect, while it could occur if you design incorrectly, is readily avoidable namely by controlling excess solar gain and other gains in the space. So again, not going to unpack all of these fully, but just giving you a bit of an idea. So some of those other barriers that are more sort of, tangible, certainly the awareness. If clients, if healthcare clients don't know about this strategy, then they're not going to ask their team for it. If they don't ask their team for it, they may not get it. They may not even be able to explore it. Air changes per hour, how do we demonstrate equivalency is unclear. And so we'll unpack that a bit more later. The inertia of the status quo, which we've all experienced. Experience and expertise of our consultant base out there. You know, Stantec and his counterparts and Greg and Sabah, they've had I guess the fortune of being able to work on DV projects and build that expertise over time. Others who haven't had the opportunity, well, you know, there's a learning curve there. We want to support that. And in terms of infection control, while many of the benefits have been exceptionally well proven, there's still uncertainties and things that we need to demonstrate more fully, and that's part of what we want to help overcome here. So gonna go back and then unpack a bit further. What is displacement ventilation? How does it work? And I'm going to pass to Tarek for this part.
Wonderful. Thank you, Alex. Very, very good introduction here. Hi, everyone. Tarek Milani. Pleased to be with you. So a little bit about, what is displacement ventilation is usually the first question we get. So the image on the left that you're looking at here is a typical patient room in an acute care facility. And typically what you'd find, and you see this in commercial buildings, you see it in institutional buildings, is overhead supply, or what we call mixing ventilation. So in mixing ventilation, supply comes from a high level. It's at a relatively high velocity, relatively cool in order to get a cooling effect. And it churns up all of the air in the occupied space. And we'll talk a little bit more about that in a minute. And there's also a high level exhaust. So you mix all the air in the space and you relieve that air at a high level. And that's overhead mixing ventilation. For the next slide, enter displacement ventilation. And the image on the left, we'll talk about in Nanaimo Regional General Hospital in a minute here, but you're looking at a room that has displacement ventilation. So in displacement ventilation, you've got a grill in the wall, and from that grill, you discharge relatively slow, relatively cool supply air into the space. And it's not as cold as it would be from an overhead mixing supply. But it comes in at a low level and it kind of pools at the floor level or at the lowest level. And as that cool air comes into contact with heat sources like people or lights or equipment, it creates a thermal plume. And that plume comes up in the individual in the image there. It wipes them, taking away with it as it rises heat, contaminants, pollutants, moisture, and it takes that to a high level, and then you exhaust that air at the high level from the space. And we'll talk in a minute a lot more about the details of how the energy flow is and how the infectious aerosol flow is. But fundamentally, the difference between mixing ventilation and displacement ventilation, or MV and DV, MV, you have high level supply and you're mixing all the air in the space. And in DV, you have low level supply and you have directional airflow within the occupied space.
I'm going to keep going, Tarek, and Sabah also.
Sure. Yeah, sure. So as we get into now thinking about the thermal profile inside the space as we shift from MV to DV. So in MV, you're completely conditioning the entire occupied volume of the room. So from the ceiling level down to the floor level, it's monolithic, and you're completely conditioning it to what we call the room temperature. And that's important because as you're supplying air from a high level, it needs to go through what might be a stratified zone or a warm zone. It needs to cool that down in order to get to the occupied space where you want to see the effective cooling. Displacement ventilation, image on the right, you start to see more of a stratification of the thermal loads within the space. We all know warm air rises. So the key here is letting that warm air rise. And one of the fundamental aspects, and we'll talk about it more, there's some more information on it, but one of the fundamental aspects is with displacement ventilation is not worrying about what the temperature is at the high level of the room. Really, we only care about the temperature in the occupied space. So the first 6 feet or so of the room at the lower level. That's where we want to provide cooling. Most of the heat actually rises up out of that space and collects at the high level of the room. So in displacement ventilation, you don't actually incur the cooling load required to condition all of that space because you're saying, I don't mind that it's warmer at the high level, and we're going to let that exhaust out. So that's some computational fluid dynamic modeling that we're looking at here. So I'll pass it to you.
Sure, absolutely. Hi everyone. I think this is a great image to show us what is happening in displacement ventilation. The picture on the left, basically, we are pouring the water at the very top, and this creates stirring effect, basically mixing all the water there before the water leaves. But if we look at the image on the right, showing us how displacement ventilation works, we are introducing the water at low level and slowly rises, pushing all the contaminants, like the orange dots there, out of the water there. I think this is a great image to demonstrate how efficient displacement ventilation is, especially when it comes to infection control. Because if we look at the picture on the left, you can see the patient lying there on the bed as being introduced to air that mixes everything in that room, versus the picture on the right is clearly showing the air has a clear path, pushing the contaminants away from everyone in the room, including the patient, to the ceiling. Thank you.
Thanks, Sabah. I I studied environmental engineering, and within that, there was a very familiar phrase within that context, which is the solution to pollution is dilution. And I didn't think about that expression for many years, but someone actually pointed out to me that, oh, interesting. It seems like that is the sort of philosophy behind mixing ventilation, which essentially it is dilution of the contaminants, and, you know, a lot of dilution in some cases, which is, you know, great, and we're comfortable with that. However, it seems more appropriate to me in a healthcare setting that we are taking more of a philosophy of bringing the cleanest air right to the breathing zone. So let's keep going. And there's some more info there that we won't unpack just now. So unpacking ventilation rates a bit more broadly, I'm going to invite Greg to tell us a bit of a story about ventilation rates here.
Bouncing around in this diagram illustrates how uncoupled science is to the actual selected air change rates in healthcare facilities. It more reflects the cost of energy or opinions at the time or cooling demands. And so recently there's been a study of a hospital where they tuned down the ventilation rates quite a bit and measured the air quality and discerned that, in fact, we are over ventilating healthcare facilities, from at least from the contaminant standpoint. From virus spread, this is the area that's of most interest right now. So you can see that we had 1.5 air changes way back in the 1959, and we went up to now 6 air changes. We dipped down when the price of oil went up. These ventilation rates reflect more the requirements for cooling, with the exception of rooms like where there's surgery taking place. There's a need for moving the air at a larger amount to make sure that there's no possibility of transfer of germs from the open wounds. Anyway, these numbers are being examined right now by both ASHRAE and CSA as to what is the scientific basis of this, and should we not be determining what is appropriate on that more rigorous basis.
Yeah, I'll just, for anyone not familiar, so ASHRAE stands for the American Society of Heating, Refrigeration, and Air Conditioning, I think, and it's a bit equivalent to our Canadian CSA or Canadian Standards Association to some extent, or there's ASHRAE is a huge organization with a lot of resources, so they do a lot of research, and we often take and adopt what they have here. So just to unpack some of those acronyms, and that first graph that Greg was speaking to is, you know, ventilation rates for sort of various building types, and then this one is more healthcare specific, but sort of a similar thing happening there of trying to figure out what is the most appropriate ventilation rate. And then this one I'll start, and then Greg, I'll let you expand. To make it a bit easier for folks that are less familiar with sort of air change rates, liters per second per meter squared, and so on. So an air change per hour is the idea. If you think of the volume of a room, if it's 1 air change per hour, that means in 1 hour you're completely changing that volume of that room. So ASHRAE ventilation rates are usually like they're based on liters per second per person or liters per second per meter squared. So it's not like a direct one-to-one comparison to air changes per hour, but did some quick calcs here to take example rooms, you know, because the height and so on matters, and just give you a bit of a sense of the range of the total outside air in the orange here for, you know, residential, classroom, office versus various healthcare type spaces from, you know, operating room to patient room. And so you can see, get a bit of an intuitive sense of the magnitude of the difference of the outdoor air, and then the magnitude of the difference of the total air. And so for those that are less familiar, just trying to sort of hit home this key message that part of the reason that healthcare is so energy intensive is because of these huge, like higher outdoor air requirements and higher total ventilation requirements. And part of what we're pointing to here is that the currently prescribed rates may not be the optimal, or at least all signs are suggesting that they're not. Greg, do you want to unpack that further?
Yes, the blue line indicates the total air change rates, but you can see that's quite a bit different than the outside air. So that means a lot of air is being recirculated. That is mainly because it enables there to be delivery of sufficient cooling capacity, but also the delivery of air that's been disinfected. Now, this has been an issue in healthcare for some time as to the advisability of recirculating air. Are the filters sufficient to actually prevent virus circulation? They're typically not sufficient to avoid gases, medical gases and odors between spaces. So that's another trend right now, is to go to 100% outside air where possible, depending on the kind of space that's being served.
Great. Thanks, Greg. And then just touching back on, Greg, I'll let you speak to this one.
Yes. So Florence Nightingale was quite the scientist as well, and she actually studied the metabolic CO2 levels and determined that on a typical ward, 2 air changes an hour would be about right to be able to remove the CO2. CO2 is a good indicator of required ventilation because it also is proportional to the heat given off by people and also the moisture as well. So she was very insightful to be declaring that would be the design goal. I'll just point out that this is assuming the number of occupants in a building, and I think that we're moving towards what the code suggests is better practice, which is to have demand-controlled ventilation, particularly based on CO2. So you have some idea of how many people are in a room at a time, and you can increase the ventilation rate according to that occupancy.
Okay. All right. I'm sure it's a question in people's minds, you know, what spaces in a healthcare context are appropriate for DV? And the answer is not all of them. So let's Sabah speak to this one.
Sure, absolutely. In this picture here, we are looking at a typical patient room, but this picture is from Nanaimo Hospital, and when we designed Nanaimo Hospital, about a little bit more than 2/3 of the entire hospital was designed to have displacement ventilation. But as a team, we were very aware of the ventilation requirements of every space, and we worked with the clinical staff to ensure that we keep that in mind. And I'll give a few examples. In the psychiatric ward or psychiatric unit, we still used displacement ventilation despite all the challenges. For example, everything in those rooms have to be anti-ligature, so it had to be made of a very thick gauge of steel, something that the manufacturer of these displacement ventilation diffusers don't usually make. So they made some custom ones for us with thick steel, and they drilled holes. But there are areas where we as a team decided to not use displacement ventilation. For example, in the trauma rooms or the isolation rooms, or in the shops. And there are many reasons for that, of course. For example, in the surgical suites or the isolation rooms or the OR or the trauma room, these are all rooms that would have exhaust air at low level in the room, which doesn't work with displacement ventilation. Displacement ventilation, as Tarek and Greg and Alex explained earlier, have the exhaust at high level where the hotter air start rising to the ceiling and get exhausted from there. So keeping that in mind, when we designed those rooms, we decided displacement ventilation is not appropriate for them. For the maintenance shops, also because they had big, large saws, like electric saws with lots of dust, with the air possibly moving very fast in those areas, it was not appropriate to use displacement ventilation. But again, if we look at the left, we can see all the spaces which usually represent the majority of the areas in hospitals. So even though the list on the right may look longer, but that list only represents a smaller portion in almost every hospital. The list on the left, even though it may look shorter, that represents the majority of the spaces of every hospitals, like patient rooms, office spaces, waiting areas, even the waiting areas. You can see a cylinder right beside that opening, that door in the back, the one with the bottom green part and the white. That was very unusual diffuser to be installed in that area. It looks like a cylinder. We supplied the air from below because the architect, of course, wouldn't like big ugly duct to come from the ceiling. So we worked with the team, and we were very fortunate, very lucky to work with an open-minded clinical staff and entire team at VIHA, Vancouver Island Health, and that's how we achieved what we achieved there. Thank you, Alex.
Well, all right, I'm going to ask Tarek to give us a bit more insight into the infection control.
All right, let's get into some of the fun stuff. Thank you, Alex. I'm not sure if this one animation works, but when we first deployed displacement ventilation, there were a number of reasons we looked into it. And one of the primary reasons was energy savings. And we'll talk a little bit more about how that was. But we knew inherently that there was an infection control benefit by virtue of having that directional airflow and having aerosols rise to the high level. So we modeled it. We worked with a PhD student at UBC. And what you're looking at here on the screen on the left is a room with prescriptive 6 air changes per hour and overhead ventilation. So this is what you traditionally find in a patient room. And you can see as somebody exhales or as they cough in this example, the room is encompassed and enveloped with aerosols that reach everywhere, which we'd expect. Overhead mixing, the blender idea, you're fully mixing the room. On the right, we were pleased to find that the directional airflow was capturing the aerosols. And it was depending on where you placed the grill and the exhaust grill. And if you placed it above the head of the bed, you were able to direct that aerosol discharge and maintain the caregiver zone and the family zone from being exposed to those aerosols. So you go to the next slide. We did work, CFD modeling is only as good as the inputs you put into it. So we did take a lot of time and attention to make sure that we were able to validate our results. So we set up full mock-ups in situ to demonstrate that what we were finding was correlated with the empirical evidence. And it did hold true. So it was really great to see that what we were expecting to find from an infection control perspective in the model, we were seeing in real life. Let's go to the next slide. So a couple of details here from a source. So there's a really good study that came out just this year, 2025, and it recognized that it's difficult to understand what's happening in a room. There's a lot of complexity that goes into the heat sources, the envelope of the building, the placement of equipment, and everything that needs to be there. So it takes a lot to understand it. But really, if we try to take a step back, there's we can break it down to a bit of a simplistic model, and let's take it into two aspects or populations. The first is recirculation of air within a space. So if you have air that's recirculating at the macro or at the micro level within the space, you can find that you're spreading contaminants, and there's colony forming units, and there's things we can look at there. We're not able to filter that air out, and it's building up within the space. The second population is exhaust of air. So rather than recirculating, and even maybe we might say recirculating and then filtering is another thing that we can look at, which is a growing body of work. The other idea, though, is let's capture that infection, those infectious aerosols, and let's evacuate them from the space altogether. And what's neat with displacement ventilation, we saw the thermal plume, and we saw in the model just now how you can evacuate that. Not only are we taking out infectious aerosols from the space, we're also able to remove heat from the space. We're also able to remove humidity or moisture from the space. So there's a couple of things here that really work together as we start to approach, as we try to strive for infection control performance and improvements. Go to the next slide. So I'll keep flowing here. So a couple of things to set the stage. So Alex mentioned ASHRAE, American Society of Heating and Refrigeration Air Conditioning Engineers. And what we see is in the standard, it's actually a code in the US and in many regions, it's applied through the building code. There is an exemption that allows you to apply displacement ventilation. And basically what this says, it was an addendum to one of the standards. Basically what it says is that if you're using displacement ventilation in a Group D diffuser, you still need to provide the prescriptive 6 air changes per hour. That is a requirement for air changes in a traditional patient room. However, when you're using displacement ventilation, we will calculate that 6 air changes based on the volume from the finished floor to 6 feet or 1.8 meters above the floor. So that occupied zone, that's the area that we want to maintain the 6 air changes per hour, because we accept that the rest of the air is going to stratify, and we're not as worried about that the air change rate in that space or in the above space where it's not occupied and it's not in the breathing zone. So that was a really nice acknowledgement, and allows for the application of displacement ventilation. So now we're looking at the Canadian standards. So Canadian CSA group, and this is CSA Z317.2. And it's referenced in the building code, so it gets applied to our projects when we design and renovate our health facilities. The column that's highlighted in the red is the minimum total air change rate requirement for spaces, depending on the typology. And you can see that 27.1, 27.2, and 27.3, there's still a minimum total air change rate, 6 air changes and 4 air changes, a little bit of difference in the type of how you're providing your system, its configuration, and the facility you're in. But regardless, there's a prescriptive minimum air change rate. So if we keep going, and that's independent of the air handling system that you have, or the type and configuration, mixing versus displacement. So there is a clause, however, though, 611.23. And in short, it says, and it's a double negative, so I'll read it both ways here. The use of displacement ventilation shall not be used as rationale for decreasing air exchange rates unless the engineering studies have demonstrated an equivalent level of safety. So what that also says is when using displacement ventilation, you can reduce the prescriptive total number of air changes per hour, provided you've done an engineering study that demonstrates an equivalent level of safety. So we saw in the modeling that we just showed that there is a benefit in displacement ventilation, and you can kind of just take a step back and say, well, if one system mixes all the air and doesn't remove the infectious aerosols, and the other system has a higher efficacy of removing infectious aerosols, I shouldn't need the same prescriptive air change rate in order to provide an equivalent level of safety. With DV, I should be able to reduce that rate. So there's something that's really important there to understand. We'll keep going. So now let's talk real quickly about energy performance. So with overhead mixing and ventilation systems, we have what's called a reheat load. So you've got a central air handler that's providing cool air to all spaces, because you might have a meeting room, you might have another space that has high interior gains or equipment loads, and it needs cold air. For everyone that doesn't need the cold air, typical systems will have a reheat load, and you're basically going to warm that air up, the supply air up into the space, so that you don't overcool it. It's kind of fundamentally how the system works. And based on the amount of air that you need to provide in to meet that prescriptive air change rate requirement, you might have a significant reheat load. And from a typical hospital here, it's almost half the building's energy consumption is on reheat. So we keep going. So with displacement ventilation, we talked about on the left there, the middle image with the blue, how cool air, you're going to supply cool air and it's going to come in at a low level. It's going to kind of cool, and then as it plumes, it goes up. You cannot provide warm air with displacement ventilation. So that's one of the nuances that you have to be aware of. If you provide warm air for heating, let's say there's an envelope heat loss, that air will just plume up and rise. It'll short circuit. It'll lock up. So you need to have a decoupled heating system with displacement ventilation. And typically we provide that with reheat panels. So if you're able to use that clause that we showed on CSA to reduce the number of the amount of air that you're providing to a space, so you're not over ventilating it anymore, you're just providing as much air as required, you avoid this requirement to reheat it to protect against events overcooling, and you can now provide your reheat load directly via perimeter radiation, and you can eliminate reheat altogether, which is a very enticing aspect to the building engineers who are trying to reduce energy performance. We go to the next slide. There's a lot here. I won't unpack it all. I'll stay at a high level, but it's more provided for posterity and those that really want to dive into the details. But what I want to draw your attention to is the image on the right, the thermal image. So we know this heat rises, and you're seeing this here in an example. And when you study displacement ventilation, what you find, and what the equation on the left is telling us, is that only about 30% of the heat gain from occupants and equipment enters the occupied zone. Only 13% of the lighting load enters the occupied zone, and only about 18 or 19% of the envelope gain enters that occupied zone. So over 70% of the load is just rising to that high level where you don't really care about maintaining the temperature. So displacement ventilation allows you to reduce the effective cooling load by about 70%, if not more, which is very compelling again. If we keep going. There's another detail here, and again, I'll try not to go into too much of the weeds here, but with displacement ventilation, I'm not providing air as cold as I would in an overhead mixing. Overhead mixing, I'm driving it down from the ceiling level. I'm coming through all those high-level thermal gains. Typically, I supply about 55 degrees Fahrenheit supply air in order to meet the cooling loads. So I have to run a chiller to make 55-degree air anytime the outside air is warmer than that. Because if the outside air is 55 degrees or cooler, I'm just going to use outside air for cooling. That's the way it goes. With displacement ventilation, you're usually providing supply air around 68 degrees Fahrenheit. So by virtue of that, I can now use outside air for what we call free cooling for much more of the calendar year. I don't need to run a chiller to cool down supply air to provide air conditioning. It's like opening the window when you're warm, but it's kind of fall or spring outside and you've got some cool air. So that's another really enticing benefit of displacement ventilation. Keep going. Another detail here, it's the fan law. If anyone ever wants to take me for coffee and talk about fan laws, I'd be happy to. But when you run the math, what you find is just the way the physics works. If you're able to reduce airflow by 50%, you only need 1/8 of the amount of energy to run your fans to move that 50% airflow. There's an affinity there. It's a fan law. And it's another really compelling case to say, hey, if displacement ventilation provides equivalent indoor environment for thermal and for infection control at a lower air change rate or lower air volume, there's all these cumulative impacts that allow me to reduce the energy consumption of the building, and in turn reduce carbon emissions and everything like operational costs, capital costs, everything that goes with that. Great.
So, in the interest of time, Sabah did already speak a bit about this project. I'm gonna kind of skip over some of these slides, and here's just sort of unpacking again how we avoid reheat And I'll just touch on the actual performance of Nanaimo. On the left here is the sort of, at the time, the BC Hydro reference, so like the code building. In the middle, it was the proposed design as modeled, perhaps conservatively. And then on the right, the actual measured data. And this was from a slide that Martina Sutherland of Reload presented. And I see the references missing there, I'll add it. But basically the key message here is that this plays out in reality with the measured performance showing a significant reduction, even greater than what was modeled. So the fan energy going down, that's the red, and then this gray is heating and cooling combined go down significantly. And I think this is where the overestimate was. The actual performance is showing even less heating required, most likely. And then putting that in the context of typical performance, and even sort of leaders in Europe, their hospital performance, and our Nanaimo example being best in line with these best performance elsewhere. So that's just highlighting that the DV works, and but also want to put it in a context of it being sort of a keystone part of a holistic design strategy. It goes hand in hand with an improved building envelope and solar control in particular. And like Tarek said, the decoupling of the ventilation load from the envelope heating and cooling loads, usually through radiant, and also heat recovery, so that usually DV is done with 100% outside air. So you can, there's an energy penalty there, but that can be overcome by all these other benefits. I think we might have to breeze past some of these slides and instead start going to the Q&A. So humidity control is a key issue. Greg was going to unpack that further. Well, I think we'll skip that for today. Capital costs, perhaps we can't skip that one. Maybe that's too important. Tarek, do you want to add a little bit?
Really high level. So if we're able to apply this correctly, we can reduce the airflow demand by upwards of 70%. Smaller airflow means smaller ductwork. Smaller ductwork allows us to reduce the above ceiling space and the floor to floor. That's a significant capital cost savings. Smaller airflow means smaller air handling units, less area in the building, smaller chillers, smaller air handlers mean less electrical service, and it trickles down. And also, if we get into the world of once through air or 100% outside air systems, we're able to delete one of the air duct distribution systems altogether, a return air system, which can be significant. And then smaller shafts, better adjacencies, better flows in the building, better views, and lower capital cost ultimately.
Great. Thanks, Tarek. And one more that I think we can't just skip over, and it's probably a question for some people. Greg, do you want to unpack a bit about this lockup effect?
Sure. So there's been a reported problem with DV in a couple of studies that tried to determine with displacement ventilation whether a system would work in a building that has a fairly high solar heat gain, in fact, a very large solar heat gain. So the major study came out of Spain and resulted in poor performance, even though the study had anticipated that there'd be advantages to displacement ventilation. So that has been identified as a problem. Almost all of the other studies verify that in spaces that don't have a lot of competition for the ventilation air to the thermal plumes, the superior performance is intact. So it's just an issue of when you're designing these systems, you may want to undertake things like applying good solar control so that you're not overheating the space. Yeah, so these are the issues that we'll be working on to bring a higher level of confidence in performance.
And Tarek, do you want to say anything further about this lockup effect?
I'd say just the footnote I'd add to it is one of the hesitations that industry has for using displacement ventilation is it does take detailed design. You really need to understand how the systems work and how to engineer it and how to apply it. Managing solar gains, managing humidity control, understanding how reheat works, understanding how to model and ensure we're providing infectious aerosol control. Those are all steps that you need to take in the design process. And sometimes there's inertia. I love that term. That and we do things the way we are. We have always been doing them because that's the way we've always done them, and they work. So there are challenges with displacement ventilation in design. You need to know how to apply it, but by no means are these issues that are insurmountable. You just need to apply, and that's apply the principles. And that's one of the reasons why we're elevating this conversation, to try and help share the knowledge that it's not as bad as it looks. It's not as hard as it looks. It's been done and it works.
Awesome. Thanks, Tarek. So with just a few minutes left here, sorry folks, we didn't save enough time for your questions. This was going to just give you a window into this research project that we're working on. We're in phase 1, moving into phase 2. I will sort of skip over that quickly. These are some of the issues that we want to help unpack further. And you know, the sort of pathways to get over, we have quite a lot of ideas about what those pathways could be, including eventually perhaps a prescriptive approach to DV that would help designers know exactly what to do and how in a more sort of streamlined way. For some reason, my slide that invites questions maybe got skipped, or maybe it's next. But inviting everyone to consider supporting this effort or getting involved in some way. So talk to us, you know, reach out virtually, join our mailing list with this QR code, and I'll also send out a link. Within that form that this QR code takes you to, there's an expression of interest to actually participate. And that participation does not require that you be knowledgeable about DV or that you be a champion. For example, if you're very skeptical, we welcome you to participate, ask the tough questions, make sure we can answer them, so on. So apologies again for leaving so little time for Q&A. There's a number of questions that have come through. Maybe I can read some of those out. I know that a number of our presenters and probably audience members need to leave in 3 minutes. So again, sort of the beginning of a conversation. A question from Douglas Courtemanche, I'm not sure if I'm pronouncing that right. Is there data to show patients cared for in a DV environment have a lower nosocomial infection rate than those cared for in an MV environment?
You want me to blast through these, Alex, real quickly? I can try to. Sure. So there is Nanaimo Regional General Hospital. We went back in, and it was the emergency department in particular, and we did post-occupancy evaluations. We did show a reduction in infection, nosocomial infections and everything that came from there. The catch is there was a lot of things that we did on that project that we really put time and attention into, including the exposure to light and daylight and courtyards and everything. So it's hard to isolate exactly what's specific to DV, but that study did show that there were benefits there. Just next question here, also from Douglas, regarding operating rooms, air walls. Yes, so in an OR, you're really trying to maintain the sterile field. So we've got laminar flow ceilings or air curtains and everything that's there. There are studies that show what DV would look like in ORs, but they don't present the same infectious aerosol control or infectious disease control as laminar flow ceilings as being the gold star. So we wouldn't want to put that in all spaces. Though there is some thought in switchable systems, like for emergency situations that you're talking about, where you can actually flip things through in case of a pandemic. Peter's got a comment here. What needs to be proven to allow DV in Canada? What types of modeling proving what? That's one of the questions. It's kind of, there's vague ambiguity in the code as to what we're trying to demonstrate. Typically, though, we're doing CFD modeling to demonstrate we're meeting the temperature requirements, the humidity requirements, and the infectious aerosol control as an equivalent level. That's what we're trying to get to. But it ends up being the discretion of the engineers of record and the architects as to what is appropriate, and the multidisciplinary team with the clinicians and the owners and facilities team to make sure we're taking that into account. Comment on wildfire smoke. Wildfire smoke is a challenge for us, no matter what type of systems we have, no matter, we're always bringing in some outside air. So typically that's dealt with through filtration. There's electrostatic filtration and there's carbon filters that we apply in order to be able to manage that. And the same thing would apply for DV. And then humidity levels, again, sometimes you'll have to dehumidify and reheat up if you really have a high humidity level. But the key is with DV, you're able to capture and exhaust that moisture before it really gets into the space. Humans are the biggest contributor to humidity in a building, and that's how we're able to approach that.
Awesome. Thanks, Tarek, for speeding through those. I know folks are probably dropping off as we speak, so thanks again, everyone. Please do reach out. There's, you know, Greg has read like dozens, if not hundreds of studies over the last few years. There's so much new research, and we're trying to keep up with it and consolidate it into the deliverables for this project. So we have a lot of information we can make available for those that are interested. And yeah, I think some of us are able to stick around if anyone would like to stick around for more Q&A, but I think our key people that can answer, some of them are dropping off. So probably can stop recording, I think. And Autumn, I don't know if you want to say any closing words.
Yeah, so you guys want to stay on and answer more questions? Is that what's happening?
I'm happy
Or
to. Got a couple minutes if there are any.
yeah, we can, if you guys want to just finish answering those, that's fine. We can stay a few minutes later, but I'll just say thank you to everyone who attended, and yeah, drop off if you need to. Otherwise, welcome to stay on for a few more minutes, and I'll just keep the recording going.
Yeah, I think there's 2 open questions, but I think we've hit them. From Peter, what needs to be proven to allow DV in Canada? What types of modeling proving what? So the code technically does allow, or the standard does allow for it now. The type of modeling and what we're trying to prove is a little ambiguous in the requirements. It just says that equivalent level of safety. So typically we're checking temperature, humidity, and infectious aerosol capture. And then how DV takes in wildfire smoke. Yeah, again, filtration. So either carbon filtration or electrostatic filtration being the keys there.
Don't see more questions coming in. I think maybe we should let everyone get to their next meeting.
Hopefully you found the time helpful and you're informed into what's coming into the industry, and you can help to advocate for it in your own regions. And feel free to ask questions and reach out, and we'd love to talk more.
Thank you, everyone.
Thanks, everyone. Thank you to our panelists. It was a great webinar. I did, just for anyone else who's sticking around, I just put a little post-webinar survey in the chat. Appreciate if anyone could take that. But have a great day, everyone, and take care.
Okay. Thank you.